All right. So if we look at the slides before going the actual algorithm here, which is just this. When somebody give you again the dynamic programming solution to some algorithm, this is going to be given to you and that's it. All right, do not expect any pseudocodes or anything. As I told you before, this is the entire solution, the entire dynamic programming solution for the problem at hand. But also what these mean, they should also be described, but I'm going to describe them to you nicely so you'll understand what those are. And by the way, also bear in mind that the recurrence relations that are here, they do not correspond to the profile hidden Markov model that we use. So some of the terms may be missing in this one. This is just to give you an idea about what Viterbi recurrence relations look like. But yeah, I'm going to now describe that algorithm to you, and we are going to solve part C of that exam questions, and you will therefore know Viterbi algorithm in detail. It's a dynamic programming algorithm, meaning that the solution is provided by using a smaller instance. It's a recursive solution, by the way. Dynamic programming means that the recursive solution is provided, but the solution is not implemented recursively, because if we implement it recursively, it's going to have exponential time complexity. But what we do is we implement it as a table filling. The recurrence relation gives us also a recipe to start filling the table from bottom up. But the recurrence relations themselves, they're going to be constructed, built from top down, but we will just starting from the base case where the recursion ends. We are going to start our filling our table. Let's look at the following assumption. At any time, or this time here corresponds to at any column of a multiple sequence alignment, or at any position of your protein sequence. The process we are modeling is in some state. So that's true for our profile hidden Markov model. Any position in our protein sequence, we are at some state. Every one of those columns in a multiple sequence alignment, they model some state. And we have finite number of states. That's also true. Our sequences, protein profile families are finite. Each state produces a single output. This one, some states produce no output, but this statement doesn't actually, I mean, it may contradict with what we have, but no output can also be considered as a single output, or the gap itself can be considered as a single output. But we are not, our outputs are not gaps here. Okay, the emitted symbols, we don't emit gap. If you look at the emission probabilities of our hidden Markov model, there was no gap in any one of those. We just say we don't emit anything. All right, in certain states like the delete state, begin state, and end state do not emit anything. But the other states, considering the other state, they produce a single output, meaning that at some time we will emit some nucleotide or some amino acids single letter. Computing, so let's look at the last one. Computing the most likely hidden sequence up to a certain point t must depend only on the observed event at point t and the most likely sequence at point t minus 1. So this assumption actually here, like, it actually gives you the solution to the dynamic programming solution. It gives you a big hint. And this is actually satisfied because where you are currently in state, let's look at this figure. If I tell you that I'm currently at state M2 and I have observed a symbol G at state M2, which state I can be before coming to M2? There are only two possible states, right? The transition probabilities here are one-step transition probabilities, meaning that where we are going to be next is determined where we are currently. So it's actually like a first-order Markov chain. What we have here is a first-order Markov chain, and meaning that the transition probabilities, in order to determine where you're going to be next, for example, when I'm at M1 right now, where I'm going to be in the next step is determined solely by these transition probabilities, which is one-step transition probabilities. If in the other case, I mean, if it was not a first-order Markov chain, for example, if it was two second-order Markov chain, you would have to look maybe more in the past to determine where we are going to be next. For example, being at M1 would not be sufficient to determine where you're going to be next. Before M1, were you at I0 or B? So if you look at two steps, second order Markov chain, you'll have to have a more complex transition probability table to indicate all the possible states that could have preceded M1 too. So, but I just wanted to state this to show you that there are more complex transition schemes. But here we have our profile hidden Markov models are very simple first order Markov chains. Where we are currently determines where we are going to be next with some probability. Meaning that vice versa, if we are currently at M2 at time point t, where was I at time point t minus 1? I could either be at M1 or D1, right? Those are the only two possibilities I could be at the previous time step. So this is basically saying this. So what is also saying that the best path that ends at M2 and emits this last symbol G, if you know the best path that ends at M1, which emitted the previous symbol, imagine before G, I have this previous symbol T in my sequence. I have a sequence, imagine for example, which looks like this, T, T, A, T, G, C. Imagine I want to figure out the best path that emits T, T, A, T, G, C from this hidden profile, hidden Markov model. Now, what I just said was, if I know that currently I'm at M2 and the last symbol I emitted is G. So currently I'm here at this sequence. The best path that ends at M2 and the last thing that emits G, if you want to figure out what the best path is, you have to compare only two things. What is the best path that ends at D1? Forgetting about the previous cases. I mean, because from before M2, you only have two choices, right? You either have to be at M1 or D1. Is there any other possible way to come to M2? No. So if these are only two possible choices, in order to determine the best path that ends at M2, all you need to do is, what is the best path that ends at D1? And what is the probability of the best path that ends at M1? And compare these two multiplied with those transition probabilities from M1 to M2. So what I'm saying is that if this TTAT, the first part of the sequence, the best path that emits TTAT and ends at D1, if you have observed TTAT up to this point, by the way, at D1 we don't have any emitted symbols, so this T, in other words, this T should have been emitted, this last T should have been emitted from this I0 state. This is also saying that, right? So the best path that ends at D1, but the last symbol that was observed was T. Let's call it, for example, if it is 0.02, okay? And imagine the best path that end at M1 and again observe the first four symbols TTAT, which means that this last T is observed at M1, which means if we have visited M1 last, the last action, the last symbol that you observe has to be emitted at M1. So what I'm basically saying is that in order to figure out the best path that ends at M2 and the last symbol is G, you need to compare these two things. If, for example, the probability of the best path that ends at M1 and observe the first four letters of the sequence is 0.00, for example, also this is 0.00 or 2. This may also be 0.002. Let's assume they are both equal probabilities. Now, I did it like this because I want to show you not these the probabilities are not the only important things. Actually, I could have multiplied this with, it could have been 3, right? If if I take 0.75% of it, is it going to be less than 0.2? No. Let's make it, oops, let's make it 0.2. Yeah, just a little bit larger. Okay, this one is 0.02, and the probability of the best path that end at M1 and the last symbol that is observed in T in both cases. So I'm trying to figure out the best path to reach M2. I need to compare these two paths and their probabilities. So this one seems to have a higher probability, but if I'm going to choose this path, I need to multiply this 0.022 again with 0.75, right? Because the transition probability from M1 to M2 is 0.75. So this multiplied with this and 0.02 multiplied with 10, whichever is larger, that's going to be my best path, the highest probability path that end at M2 and the last symbol that is observed as G. By the way, I need to also multiply, in order to compute the probability of this path, I need to multiply the emission probability of G also at M2. Okay, right now actually for this specific profile hidden Markov model, this is going to be 0 because the emission probability of G at M2 is what? 0, right? So whatever the best bet up to this point is, this basically telling that the probability of, so let me define a variable named V. Okay, so this V is that variable that I defined, and I'm going to define it as the probability of the best path that ends at some state, and the last symbol that is observed in that state is symbol A. Or let's give some indices today to them. For example, the probability of the best path, and we you know how to compute the probability of paths, right? We did this for that rainy sunny example. We multiply probabilities along the path. The transition probabilities, emission probabilities are multiplied one after another. So we start at begin state with a probability of 1.0. So every time we are going somewhere, we are multiplying the transition probability to go to that state. And when we come to that state, we emit some symbol, and we are going to also do that. For example, if you see that certain paths are not going to be possible for the sequence that I give. For example, it's not possible, or maybe is it possible? It is possible, yeah. From I0 to M1 is possible. So if this last T here is emitted at M1, it means that the first three letters here, TTA, must have been emitted at I0 here. Okay, so, and therefore what I'm going to do is I need to multiply 0.8 with 0.25, and then after that another 0.5 to emit the second T, and 0.25 to go to I0 again. So I need to go to I0 3 times to observe this TTA symbol. So there is a path to come to M1, but I'm not concerned about that, because the important thing in dynamic programming is that I really don't care about what the previous path is, because what I'm going to write here, the recurrence relation that I'm going to be writing here is this. Let me get a new slide. So here is the thing that I'm writing again here. The probability of the best path that ends at state Si, and the last symbol that is observed is the jth symbol of my sequence. Let's define this as that probability, all right? Which means that I may by changing these subscript, I can have all the possible states. For example, what is the probability? So this Si could be, for example, M1, it could be D2, it could be M2, it could be I1, all right? So the state can be anything. And the sequence here, for example, the first letter of the sequence, it may be, for example, that G. It may be the second, it may be a T, but if you write just GT like this, it doesn't specify which sequence in order what I mean is that there are two t's here, actual three t's, t, t, a, t. When you just write t there, which t are you referring to is not clear if you just write as the subscript the nucleotide name. And instead, we just say, for example, if the input sequence is given to us as a capital A, we just write the first character or the second character or the third character of the input sequence. Okay, so we can have something like this. So what I'm writing here underneath are just example cases, which are all possible. What is the probability of observing? The last thing that is observed is the second sequence of the input sequence, and currently I'm at state M1. What is the probability of the best path that leads to this? So this probability allows me to partially define partial paths. Okay, and I'm actually looking for this probability. What is the probability to be at the end state? And I want to observe the last letter of my input sequence. So this is what I wonder. This will give me the probability of best path to observe the entire sequence and go through the entire profile of the Markov model and come to the end state. This is what I wonder. Okay, and I want to figure out this, and along while I'm computing this, I'm going to also be keeping track of which states I visited, just like in the sequence alignment, dynamic programming sequence alignment case, to actually find the states that are visited. So this, I'm going to give you just the general solution. The probability of the best path that ends at Si, and this is Aj, is basically the maximum of all previous states. I'm just going to name them as Si minus 1, but just here it indicates the previous state that can precede Si. And so VSI Aj minus 1. Okay, so it's basically this. Okay, this is the entire Viterbi solution. It's basically saying that you have to look at the previous states only, which could have preceded Si, and pick the, sorry, not max, I need to multiply this with the transition from Si minus 1, sorry, the maximum of this probability times the multiplication with TSI minus 1 to Si is going to come here. So this is the probability of the best path that ends at some previous state and observe the previous symbol. By the way, this observing the previous symbol is going to be different for if this Si is a delete state. Because what if we have observed Aj in a delete state as the last symbol, Aj will still be the last symbol because this delete state does not, so what I mean is that if this state is a delete state and the last symbol that is emitted right now is Aj, on the right hand side of this equation, I will still remain at Aj because here, if you remember the example that I gave here, the probability to observe TTAT and end at D1 means that this T is not emitted at D1, right? So this T has to be observed in the previous state. So this is what it means that the subscript J, and I say Aj there, it doesn't go Aj minus 1 if this was a delete state that I'm talking about. So these are small important things, but in general, Viterbi algorithm, the algorithm is exactly this. The dynamic programming recurrence relation is this simple equation. It's saying that the probability that ends at state Si and the last symbol that is observed is Aj, let's define this thing, is the maximum of all previous states that could precede Si. Or all, if you say all states that are this in that case, this TSI minus 1 Si will be 0. If that state cannot precede Si, it means that the transition probability from Si minus 1 to Si will be 0. So we will have 0 here in this max term, which means that it's never going to be selected. Okay, they may never be negative. Since we are multiplying probabilities, we all have positive values here for non-zero probabilities. But this is basically saying that if you know the best path that ends at some previous state, and having observed some previous symbol that ends at state, so we reduce our instance by one character, multiply this probability with your transition probability to that state Si, and look at all possible ways you can do that. Choose the maximum of those. That's your optimum, maximum probability path. Okay, so this is basically the Viterbi algorithm, and let's see what does this mean. No, this is, we're not going to see it. The code is just a for loop that fills a table. Okay, so I'm going to, it's not going to be the, I'm going to go over how we fill in this partial scores table. But as I said, when you have a dynamic programming solution, this is the pseudocode. So the code is this basically, all right? But building the hidden Markov model, I'm also not going to give you the code for that. I'm not going to show you any particular Python or C code for this. All right. So this is, you'll have to do how to do it yourself. It's not so, it shouldn't be so difficult after you have the multiple singles alignment. Coding, especially the first part, where to build the hidden Markov model, should be simple. And also the Viterbi recurrence relations, as I said, after you know this is the entire algorithm. It basically tells you how to fill in a table of 2 dimensions, because this partial probability table has 2 parameters, state and the character of the sequence, right? I'm going to show you how we fill this table for an example in the question, the midterm exam question, but writing the code for yourself shouldn't be difficult. And in the assignment, you will have a practice on longer sequences and longer hidden Markov model. So you will build your hidden Markov model for a longer one. So this will be what you're asking is will be your second programming or written assignment, depending on how you want to do it. As I said, you can do it with Microsoft Excel or with some calculator, but you'll be able to practice this Viterbi algorithm on your own. But let's go over the exam question. But before that, let me just show you what these recurrence relations look like. So for match states, the probability of the best path by the way, I forgot to multiply with the emission symbol when we are at the match state. So, but if you look at this max part, it's basically saying the best path, the probability of the best path that end at the match state U, and the last symbol that is observed is the ith character of my input sequence X. So it means that if this is the last symbol that is observed, I have to emit this last symbol at the match state. So whatever the emission probability is, I need to multiply it. Whatever path that is preceding this, I need to multiply it with the same thing. All right, ith symbol is emitted at the match youth match state. So I have to emit these symbols. Now, in order to find the best path, I need to compare these 3 things. Why do we have only 3 things here? Because it assumes that in this hidden Markov profile, hidden Markov model, these are only the 3 states that can precede a match state. Is that so? Let's take a look at this hidden Markov model template. So where is it? So I have a match state here. What states can precede a match state? The previous match state, the previous insert state, or the previous delete state. All right, so these are the 3 possible incoming arrows to a match state. That's why this one has, in the recurrence relation, that's why these are shown only. You could have listed, in this max term, you could have listed the entire set of states. But in that case, this transition probability from match state, of the transition probability from that state to this match state will be 0. So there is no need to write them in this equation. So these are, the right-hand side shows only the possible potential non-zero transition probability previous states. Okay, so But I think there's a discrepancy here for the insert state. So an insert state could be preceded by it's the same by itself, by the match state, but it can also be preceded by a delete state. That's the missing term here. Okay, if you go, let's go quickly go ahead and take a look at our possible preceding states of an insert state. If you look at the insert state, there are three incoming arrows, one from itself, self transition, one from its corresponding match state, and one from its corresponding delete state. So it's possible to precede an insert state with a delete state. This was not uh, given as a term in the second term that's for the insert states. Okay, so it means that Viterbi recurrence relations is missing a term if we're going to use this particular profile here, the Markov model. And you don't need to memorize these formulas at all. All you need to do is, what are the preceding states? Okay, if you're in a question, if you're asked this in a question, the only thing you need to do is, what are the possible preceding states of a state that I'm currently trying to figure out? For example, if you try to use the insertion state formula for this I0 state, you see that it doesn't work out. There is no match state that is preceding this I0 state. Actually, there are only two things that are preceding: the begin state and itself. Okay, so when you're writing the Viterbi recurrence relation for I0, the previous state can either be I0 or begin. It cannot be a match state or some other thing. Okay, so it's going to be you have to just, the main rule is that whatever the right hand side of this Viterbi recurrence relation shows whatever preceding state possible leading to this state that you're looking for, you're trying to compute the probability for. And if you look at the emission probabilities are the background emission probabilities for the ith symbol, or you are just going to use 0.25 here. And if you look at the delete state, there is no emission probability for the delete state because we're not emitting anything at delete states. There is no symbol that is emitted at delete states, so it's not written here. And another important thing, which is a result of this observation, is that the ith symbol that is observed at delete state du does not mean that ith symbol is emitted at du. Ith is the last symbol we have observed up to now. Okay, so we have observed certain symbols, and xi is the last symbol we have observed. When you're currently at delete state, it means that that ith symbol xi should have been emitted at some previous match state or insert state, because delete states do not emit anything. Therefore, if you look at these recurrence relations, although the previous ones, match and insert state, it reduces the observed sequence to 1 to xi minus 1. In the delete state, we still have xi in the recurrence relation because that xi should be observed in the previous state, because delete state do not emit any symbols. That's the main reason. And also, if you look at these equations, the begin state or the end state are not written here, but in general, the general term is just this. Whatever state is this and whatever symbol is this, it's going to be the maximum of the transition probability from the preceding state to that state times the best path. So this is where it becomes recursive. Okay, this is a recurrence relation because it asks what is the probability of the best path that ends at that preceding state. The only thing that is remaining to actually be able to apply this algorithm is, what is our base case? What is the trivial case where there is no recurrence? Okay, well, the base case is the equations where we don't have any recurrence relation, which is our base case in this one here basically is the probability of begin and an empty symbol, observed nothing, or you may call it x0 if you want, which is or empty string. The probability to be at the begin state and having observed nothing yet is equal to 1.0. This is going to be our base case. And another thing is, the probability to be at the begin state and uh, having observed something where I is greater than or equal to 1, this is also 0, 0.0, which means that you cannot be at the begin state and have observed some symbol of your sequence. It means that you have to always start from the first letter in your sequence. You cannot start at an arbitrary sequence, but you can actually make this non-zero if you want to have like a not a global alignment, but a semi-global alignment in which you allow to have your sequence matched starting at an arbitrary character. Okay, so that's a variation of the original profile hidden Markov model. But in the original profile hidden Markov model, which is for global alignment, we have to start at the first character. Therefore, being at the begin state and having observed some ith symbol of our sequence will have 0 probability. Okay, we will always start with empty string with 1.0 here. Another thing is for match some trivial probabilities. If you're at a match state or some insertion state, the probability to be at that match state and having observed empty string is also 0. Or if you cannot be at, or let me write it here, x0 to indicate we haven't started the sequence yet. The probability to be at the insert or match state and having observed nothing, those probabilities are all 0. These are trivial probabilities. But let's try to solve our problem and in the exam and in the last 15 minutes. And I hope the application of this Viterbi recurrence relations will be clear then. So we need to get ourselves our model. I'm going to copy it from here. All right, that's right. So the solution that I had done, which is actually the same thing, right? If you look at this model, it's exactly the same thing we had done on GIMP, but I'm just going, because since I have written a lot of things on GIMP, so I'm going to just copy the one which is here. So I copied it. Let me copy it over this here. Let me make it smaller. All right, it's readable. Okay, scale, then move it to here. So just for my reference, I did this in part A. Now I'm going to solve this question. Let's take a look at what does it say in part C. It says A, B, and C. The GA, so find the most probable path that produce the sequence GA from here. Okay, our goal is to align GA, which was not part of one of those 5 sequences in the multiple sequence alignment, to this profile hidden Markov model. So in order to do that, this is what I do. I build my Viterbi table. The Viterbi recurrence relation basically tells me I'm going to have states and these sequences. So I write this, the empty string GNA, just like in dynamic programming of protein pairwise sequence alignment. I write here, I have a table. I will have a table here. This time, the table's columns will be these sequences, okay, the letters of the sequence, and the rows this time are going to be states. And there is no order of these states. There is no total order. For example, do match states come before insertion state? It doesn't matter. So here, what I mean is that I can write begin here, and then I can first write the insertion states I0, I2. Okay, so the order of these rows here do not have any particular meaning. We're not going to, when we're filling in a particular cell of this table, which neighbors or which previously computed cells we're looking at is not given by neighborhood relationship. It's given by those recurrence relations. All right, so I'm going to have M1, M2, D1, and D2 like this. And the final thing is the AND state. Okay, these are the states I have, right? Do I miss anything? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now this is a table that I'm going to fill in. And what I'm looking for, my answer will be in this last cell that is here. Okay, so if I compute the value of this cell, the probability to be at the end state and the last symbol that is observed is A, then I'm done. Okay, by the way, this being at the end state with empty string and G, these two entries here at the end state, we don't want this, so I can just label them like this because I don't want to compute them. I ignore them because I don't want to come to the end state and having observed G as the last symbol, because that will be a premature alignment. One of the sequences is not observed yet, which is one of the letters, which is A, is not observed yet, and you come to the end state prematurely. So we usually ignore these columns here. Again, if you're going to do semi-global alignment, for example, in which you want to ignore the gaps at the end, you may also want to take a look at the probabilities that are here. But right now, this is the probability I wonder. And here is how I initialize it. This is 1.0, 0 like this. And I don't want to, and these are 0 probabilities. Now, and also, these are also 0, 0, 0, 0, 0, right? Because you cannot be at an insertion state and not having observed nothing yet is impossible. If you're at insertion state or M1 state, you must have emitted some symbol, so you must have observed something. You cannot be at the first x0 and 0 string and observe nothing. Now, what about D1 and D2? Is it possible to be at D1 and not observe anything yet? It is possible, right? Because if there's a path from begin to D1, and in the general hidden Markov model, there's a transition actually from begin to D1. Imagine there was a sequence which didn't have anything in that insertion part and which skipped M1 and M2. And in that case, we will have these transition probabilities from begin to D1, and these would be non-zero probabilities. But if you look at our delete one state, you see that it's preceded by an insert state. And therefore, without actually computing anything, I can also write zeros here, or D2 state is preceded by M1 state. So if they are preceded by I0 and M1 state, it means that some symbols have to be observed before coming to them, and I can write D1 and D2 0 directly. I know that when I'm going to do the equations, they will come out 0 by looking at the hidden Markov model. Now, here is I'm just going to fill in this remaining ones, which I will be using recurrence relation. So let's look at the first one. What is the probability of I0G? Okay, I0G, I0 is preceded by either I0 or begin, right? Therefore, I'm going to, and this G is 0.25, emission probability at an I0, 0.25, equal emission probabilities. And I'm going to take a look at the maximum of two things, which is VI0 nothing, all right, because before G, since G is the first character, so if you observe this G in this I0, in the previous state, if the previous state is also I0, it has to be empty string, because before G we have this is the 0 symbol, and which I already know that that's 0. So whatever this option is 0, and I'm left with my other single option, which is V begin empty string, which is 1. Okay, so therefore VI0G is going to be 0.25 directly. Is it going to be 0.25? No, I forgot something here again. which means that you may also forget it. It's forgettable entity here. The transition probability from begin to I0. The transition from begin to I0 should be multiplied with this 1.0. In other words, I need to multiply 0.8 with this, which is going to indicate transition from begin to I0, and then emit 0.25, which is G at this. So in other words, I need to compare just two things. I need to compute two things just for the preceding states. Compute the probability. Both of the probabilities were already in the table. 1.0 and 0.0, they are already on the table. So by looking at these two values and computing the transition probabilities with them, I choose the maximum of those, which is this one, and 0.8, and I multiply it with 0.25 to find the best way to have this probability. Now, what about we can fill the entire first row, because the only preceding states of I0 are I0 and begin, and all the entries that I need are here. For example, in order to fill in this entry, the I0 A, okay, the I0A, I need to compare two things again. The I0G or V begin G. Okay, so these are the two possible things that could have preceded I0. Those are the only two possible things. And one of them is again 0. You cannot be at the begin state and observe symbol G. So this one is 0. This one is the non-zero thing, which is just the value right next to it. So I'm going to multiply it with the transition probability first, which is 0.5, and then the emission probability of A in that thing. So it's going to be multiplied by 0.25 again. So whatever this value is, let's call it, for example, P. I multiply P with 0.5, the transition probability from I0 to I0, and then the emission probability of A in that in I0. So this becomes the best path that ends at I0. So I filled in the first row. Let's come to I2. In order to compute I2, what are the preceding states? Delete 2 and I2 and M2, right? Oh no, it's not M2. What is this here? Yeah, after M2, there I can go to I2. So do you know the probabilities about M2 or delete 2? Not yet, all right? So therefore, the second row is not the one to be computed next. What can you compute next? For example, look at M1. M1's preceding state are I0 and begin, and you have all the probabilities about begin and I0. So you're ready to compute the probabilities for M1. What about what is M1G? M1G, the best bet that ends at, by the way, M1A is directly 0. Why? Because the emission probability of A at M1 is 0. So whatever the best preceding path is, this one is going to be 0. And what about M2? I can only observe C and T at M2, and none of my letters here are C or 2. So what does it tell you? There are going to be zeros here at M2, right? Why did I put M0 and M2 again? Let me repeat. The probability of observing, if you look at this, the probability of best path at ending at M2, and the last thing that I observed is at G. If you look at the emission probabilities at M2, it only contains C and T. The others are 0. Therefore, the emission probability of G at M2 is 0. Therefore, whatever the max part is, this is going to be 0. And the same thing for VM2A. It's also 0. All right, so these two are 0 because the emission probability of A at M2 is 0. All right, so let me erase this quickly. So let me erase these parts. Okay, now I'm erasing Yeah, maybe this much of space is enough for me. Oops. So somehow I again put it outside. Yeah, let me decrease the size back to 2 and get my pen back. All right, now let's, so M1A was 0. Let's compute this one. What is the probability of best path that ends at G at M1? Emission probability of G is 1.0 M1, so 1.0 times the maximum of two things again. M1 can be preceded by two things, and these are VI0, but since G is emitted first, I'm left with empty string for I0 and begin this multiplied by the transition probability from I0 to M1 and transition probability from begin to M1. So we know that this one is already 0 because I0 empty string is 0. So it's only this also leaves. So this is a very simple, small example that every time I'm comparing two things, one of them is 0. I'm always left with one option. But we are going to see that for certain cases, maybe we're not. This is not going to be the case, especially for this A. There may be more than one path to observe. It's maybe possible to observe it in two different paths. What is this? This is 1.0 and the transition probability from begin to M1 is 0.2. So this is what I'm going to have here is 0.2, right? Because the emission probability is also 1.0. All right, so then after M1, I can also compute D1 directly. I0, its only preceding state is I0. I already have one option. So I can also compute D1s. The probability to observe G at D1, the probability to observe G at D1 here is equal to, I have only one option. And as you can see, I have to look at VI0G. So this is VI0G. G remains as G because delete one state doesn't emit anything. So this G must have been observed at the previous state. And you look at I0G, which is this value which I called P. Therefore, what I'm going to write here is P times 1 over 8, which is the transition probability from I0 to D1. Okay? And this one, whatever it is, so it was, let's call this probability Q. And this one simply will be Q times 1 over 8, whatever that. So the probability to observe A at D1 means that you have observed A previously in I0 state. We have this probability as non-zero. Multiply it with your transition probability to D1 and you fill in this one. And this one is going to be 0 anyway because for D2, the only preceding state is M1, and M1A is already 0. So D2A therefore should be 0 as well. And D2G, there will be only one possible path, which is going to be this 0.2 times the transition probability from M1 to D2, which is 0.25, which is here. Okay, 0.25, this one to here. Therefore, 0.2 times. 0.2 was the best path that ended at M1 and have produced this G. And D2G is the same thing, 0.2 times 0.25, the transition. So we have filled in most of the entries. The only thing that is left is I2. Let's quickly go over them too. And for I2G, first of all, the self-transition for I2G is going to be 0 because I have to emit something beforehand. So, and therefore, and D2, so what I'm looking for is the probability of, so D2 empty. So let me just write it here, I2G. In order to do that, what I'm going to take a look at is, what is the probability to observe D2 empty set? I2 empty set. If I, and the other preceding thing is M2 empty set. So since all these probabilities are zero, this should also be zero here. All right. And the final thing that is remaining here is I2A. For I2A, let me write it here. I now have to compare D2 empty set, which is zero, not D2 empty set. Before I2A, what do I have? D2G. Now all these empty strings, they're going to be converted to G's like this, and this one is the zero probability here. D2G and M2G are compared, will be compared. So D2G is this, and M2G is this one. Oh, sorry. Oh, M2G was zero, right? So it's not possible either. So M2G is possible. So the only possible path becomes this one. So you're just going to, whatever this probability is, you're going to multiply it with 0.25 and multiply it with the transition probability 1.0, D2 to I2 1.0, and you're going to write it like this. And the final thing, you're going to compare whether it's possible, which probabilities are larger. Let me go directly to the solution before I stop today's lecture. If we go to this one, you see these are the same probabilities. I2, this one is non-zero, and this and the and one is going to be comparing two things, whether by the way, it's not going to be comparing two things. Let's see, since M2, oh no, M2A, let's take a look at what we did for M2A. Yeah, they're all zero. So it's not possible to come to the end state from M2 state. So the only possible ways of coming via I2. So again, all I need to do is whatever probability I have computed for I2A, let's call it R, I'm going to multiply R with 0.6, the transition probability from I2 to end, to compute my final result. And that's it. And all these back arrows, the back trace tells you where you got this maximum, where you got this value. For example, we got this 0.2 by coming from the begin state. So there should be an arrow to the begin state. So you can backtrack, just as we did in pairwise sequence alignment, dynamic programming. We can backtrack to figure out which states are actually visited. So for this particular sequence, we started with begin, then went to M1, then D2, then I2, then came to end. And this is the only possible path. Therefore, actually, you don't need Viterbi algorithm to do that. You can do it by manually with no algorithm to see that this is the only possible way to align your sequence to this profile. But in general, there are multiple ways to align your sequence to a profile. And therefore, in order to find the best of them, you have to run this Viterbi algorithm. And it's a polynomial time algorithm. Polynomial is a number of length of your sequence multiplied by the number of sequences in your number of states in your profile hidden Markov model. And each of these entries are computed in constant time because constant number of preceding states are there in our profile hidden Markov model. Okay, now I'm going to stop today's lecture